Now let's look back at the web of ideas that we keep referring to, and I've been talking about how algebra and geometry are essentially rigid subjects, or there's a lot of rigidity to them, and I want to contrast that to topology, and calculus has already come in a bit, but I want to really bring in topology as a major player here. So topology is the study of shapes where we're allowed to deform the shapes and consider them as the same, consider them unchanged. So here's three examples. Here's a sphere. That's just the surface of the sphere, not the interior, so it's a two-dimensional surface sitting in three-dimensional space, is what we're trying to picture. That's the same to a topologist as if you kind of stretched out three parts of it and made it a very unround sphere. A geometer cares about the roundness, but a topologist doesn't care. And so this is just kind of stretching it out into a kind of as if it was made out of Play-Doh or something. Similarly, a pair of pants to a topologist is the same thing as take a sphere and puncture it, take three holes out of it. And these three circles, it turns out, it's a little hard to picture maybe the first time you think about it, but these three circles correspond to the waist and the two hems on the ends of the pants. And of course the most famous one is that a topologist is somebody who can't tell their coffee cup from a donut. If you melt down just the cup part, then there's no sort of you can go into and out of the cup without any problem. You can melt this cup part down, and what's really, to a topologist, what's interesting about it is really the handle. So in topology, just as in geometry, we still have this fundamental idea of there's a space, some sort of universe to live in, and so for any particular problem, we sort of consider that to be the be-all and end-all of existence, and then we consider objects within spaces. So let's think of this sphere, for example, as a universe for a problem, and not as an object to be studied, but as a place to put objects into. And then maybe these loops here could be the objects that we're going to study within that universe. And there's many objects that we could study, but we're going to study topological cycles, which in one dimension are just closed loops. And so here's a bunch of cycles, and here's an equivalent cycle to this one on this different picture of the same universe. Similarly, a cycle that goes around one of the pants is equivalent in this picture to this cycle here. Here it's a little bit more complicated. I've got a green cycle that winds around the handle and just for fun tries to kind of go back into the back side of the cup and then decides to come back over here. That's equivalent to a cycle going around the length of the torus like this. And then just kind of small, you can see a little cycle that's where your fingers would grasp the cup. That would be equivalent to this one. Well, it's also equivalent. All these guys, because this is topology, we basically say that a cycle is going to be the same if we start to deform it. And in fact, let me talk about that in a second. Let me just finish talking about this. For us, a topological cycle, the important thing about the cycle is it just has no boundary. So if it's a curve, it just has no endpoints. It has to be a closed curve. If it was a two-dimensional cycle living, for example, in three-dimensional space, it would have to have no edge. And an issue that I'm not going to talk about very specifically, but it's going to come up in the background a lot, is each cycle has to have an orientation. So that's the arrow. You're supposed to be a specific way you're told to traverse this cycle. So I'm going to say something that's not quite the technical definition. The technical definition is easier to work with, but just not exactly the way I want to state it. We're going to say that two cycles are the same if you can deform one to from one into another. So for example, these blue cycles, you could just take that and slide it over to be this blue cycle. And this blue cycle down here, you could deform it. The picture is not incredibly obvious, but here I've got the cycle coming around the top and then turning around and then turning around again and going around down back here. That's really just a deformation of this. It's just, if you think of this as like a rubber band on a surface, then that's just sort of stretching it out, but it's not essentially doing anything different. But what is true is that, for example, this blue cycle, there's no way you can deform that in a continuous way without breaking it and reconnecting it to be the green cycle. So here's something we can do. A big thing you can do with cycles is you can intersect them. This is really much like the case with the Bezout's theorem for algebraic cycles. So for example, you can intersect this blue cycle and the green cycle. Now you might if you think for a second, you might see something that looks like a contradiction. I'm saying that these blue cycles are the same cycle. They really shouldn't be considered to be different. There's different pictures of the same object. And yet one clearly doesn't intersect the green and one clearly does. And that might seem a little bit similar to the Bezout's theorem kind of case, and it has connections to it. What's going on here is this issue of orientation. If you actually do the intersection carefully, what you're supposed to do is you're supposed to count this intersection where blue is going up and to the right and green is coming this way, and this intersection where the blue is going in a different direction. You're supposed to count those with opposite sign, and they actually are supposed to cancel out. So to a topologist, these guys aren't really intersecting. These guys, this intersection here, there's only one point of intersection. Notice the dotted part of the blue in the back is not intersecting this green curve. There's only one intersection. It's not canceling out with anything. And so that really is an honest-to-God intersection. And notice the blue curve, it's intersecting in the same way as this blue curve goes here. Then it's intersecting the opposite way, and then the same way. These two actually do cancel out. And so when we try to deform it and try to fake it into intersecting too many times, keeping track of intersections actually tells us, no, that's not really a new, genuine intersection. So you do have to keep track of those orientations to do this all carefully. But this idea of looking at intersections and counting the intersections is a very good thing to do with cycles. In fact, we can look at multiplicity. I told you that algebra and calculus are two ways to understand the idea of a high multiplicity intersection. Like here, this is y equals x cubed intersecting the x-axis. This, I claim, is a multiplicity 3 intersection. If an algebraist says, of course it's multiplicity 3 because it's x cubed. And calculus can analyze it in terms of sort of how the thing is curving and rates of change and rates of change, etc. But let me just tell you how a topologist might analyze it. What you do is a topologist says, I don't care that this is y equals x cubed. I'm going to deform it a little bit. And so I'm going to take this intersection where it's exactly tangent right at the origin, and I'm going to push this part up a little and push this part down a little. And then this is just a blow up of the same region. So I'm going to have 1, 2, 3 intersections. These are transverse, and it turns out that it's actually very easy. If you sort of just randomly perturb something or deform something, you're going to get something that's transverse intersection, and then you just count in the ordinary way. Now, if you think about it for a second, you might think this is totally bogus, because another way to perturb this y equals x cubed would be to just raise it up, and then it would only intersect once over here, it seems. Well, remember that this is only the real picture of this curve, and if you tried to deform it that way, then you would actually have other intersections, but they'd be complex. I just chose one where the intersections actually show up in the real picture. And then there's also issues of orientation. You might think, well, wait a minute, isn't this a +1, a -1, and a +1 intersection? Isn't that really canceling down to just like a +1? Well, again, this is really something that's happening in the complex world, and if you keep track of the orientation correctly in the complex world, then you actually do get 3 non-canceling intersections. So you can see there's some real subtleties with things like complex numbers and orientation that come up. And I might sweep other stuff like that under the rug in the future. So here's a nice place to be. We're combining now topological ideas, and I'm going to combine that with what we know about algebra and geometry in the projective plane. So here's a new perspective on what we were doing before. We've got an algebraist, or sort of an algebraic geometer, talking to a topologist, and each of them is sort of free to suggest things to the other. Here's the situation. The topologist starts out and says, okay, here's a projective plane. I'm going to just draw one of my funky freehand curves that doesn't have to come from algebra, and that I'm free to deform, and feel free to ask me to deform it to be nicer if you want, Mr. Algebraist. Okay. And the topologist says, I'm going to look at this curve, and it intersects 5 times, and even though this looks like these are going to be canceling out, again, if you do it in the right way, these are really non-canceling intersections, and it intersects 5 times. And I'm going to define the notion of degree as I'm going to take my curve and intersect it with a random line and see how many intersections it has. The topologist has never heard of polynomials. They don't know what the degree of a polynomial is. They certainly don't know the calculus idea of what a degree would be. They have their own definition. And Bezout's theorem really says that the topologist definition of degree agrees with the algebraic geometer's definition of degree. Bezout's theorem says if you measure it algebraically as the degree of a polynomial, it's the same number you're going to get if you intersect it with some random line. Okay, so a topologist says, okay, I have drawn a degree 5 curve in my very rough, loose, flexible topology way. And here's a big theorem about the projective plane that kind of quantifies how much flexibility the topologist has. If some other topologist had drawn some other curve that looks very, very different but has the same degree, in other words, the same number of intersections with a line, turns out that one of those topologists, hopefully, if they're clever enough, they can figure out how to morph one into another. This is a big theorem, that there's only one number you can measure about a topological cycle in the projective plane, and that's its degree. And there's nothing else that really distinguishes it. Okay, so topologist is pretty happy. There's one number that describes all the possible objects he can draw up to the kind of deformation and equivalence that he's allowed to do. Now the algebraist has been just watching this for a while, twiddling his thumbs, and then says, hey, I want to get algebra into here. I don't really like these floppy topological cycles that don't have anything to do with algebra. Is there an algebraic cycle in the projective plane that is the same as this topological cycle? Well, this result right here suggests, this result right here suggests that it might well be true, because there aren't that many different topological cycles. There's only one for every number, namely the degree. And the algebraist knows that's true for him as well. There's various polynomials. You can create a polynomial of every degree. And in fact, we could be a little bit more precise. Okay, the answer is yes. And so a good way to try to really be pretty precise about this is just look at the zeros, look at the intersections that this curve has. It's easy to create a polynomial with exactly those zeros. If you want to know the algebra, you just take the coordinates of these intersections and take x plus or minus various things and multiply them together. That's not terribly crucial. The important thing is that there is an easy way to create a polynomial given some intersections. Again, there's some big issues about projective space complex numbers. For example, if you thought that the topologist could make these two intersections go away by just shrinking it down, progressively shrinking it, and then instead having a version that went like this, then, as I said before, those intersections would still be there. They'd just be in the complex world. Okay. So there's some issues there, but I see this as maybe the simplest, most basic toy model for the Hodge conjecture, which is a topologist you're living in an algebraic universe. The projective plane is defined in a way that algebra we know works well, and it's itself a fairly rigid object and very nicely behaved. But a topologist comes along and says, I'm going to put my weirdo flexible topological object in there, and I'm going to challenge the algebraist to find some algebraic version of that. And I'm going to let the algebraist morph it around according to the topology rules until, hopefully, they can find a very rigid object, the graph of a polynomial in this case, that matches the topological object. And the answer here is yes, you can do that. And that's really the story that's going to come in the Hodge conjecture. Okay. One thing that I've glossed over, and it's actually in the two-dimensional kind of projective plane example, it's hard to get this to fail. But remember, we are working with complex numbers here. This is a very schematic picture of what's really a 4 real dimensional space. Remember, x is a plus bi, y equals c plus di. Whenever you have an algebraic cycle, and again, this has to do with some of the things that I was talking about a minute ago about what you can't do, what you seemingly could do with this curve and you really can't do when you look in complex numbers. An algebraic cycle, because it's really defined as using the whole package a plus bi and the whole package c plus di in the equation, it's really x and y that have to appear. You can't artificially take the x apart into the a plus b and the y apart into the c plus d. To a topologist, they don't notice that. They just see 4 real dimensions and 4 numbers they could play with. And they might actually come up with something that doesn't really have a legal mix of the real and imaginary parts. So for example, if you drew a topological cycle with only the A and C parts, then that actually wouldn't work. You wouldn't be able to come up with an algebraic cycle that really matched that. Okay, so we'll return to this issue. It's going to be the most subtle thing, and I'm going to sweep it under the rug pretty firmly. But there is one sort of the main thing is it's an easy condition to check. If the topologist writes something down and secretly tries to trick the algebraist by only including the A and C and not having a legal mixture of real and imaginary parts. The algebraist can detect that extremely easily. Okay, let me talk about another issue that comes into all of this story, and especially the Hodge conjecture. Local issues versus global. Most points of a nice space, and there's spaces that are exceptions to this, but like the sphere, most points of the sphere look identical locally. If I'm an ant walking on the surface of the sphere and I'm walking around this point, it's almost the same as just walking around this point or this point. It really is the same. You wouldn't be able to tell. Okay. The only points that are different on something like this, a boundary, the ant can tell because there's one direction that they can't go or else they'd fall off. But all the other points that aren't boundaries are basically the same. Similarly, to a topologist, all these points in the coffee cup are very similar. Remember, even though a geometer would say, hey, this is more curved, it's got a very small radius of curvature or something like that, a topologist doesn't know about those kinds of concepts. Okay. Similarly, if you look at a cycle, so that's something about spaces, that most of the spaces we're interested in are identical locally. Another way to say that is you can build them by taking very, very simple patches, just like little disks here, and glue them together. It's the way you glue them together that determines the difference between some shape like this and some shape like this. So locally these are identical, a sphere and a torus, but globally they have very different properties. For example, there's no possible way you can draw a non-trivial cycle on a sphere. No matter how wacky and weird a closed curve you put on a sphere, you can always just kind of suck it all up to the North Pole and make it deform to a point, which is our notion of being trivial, of being zero essentially. Here, this cycle, this blue cycle that links around the torus, there's no way, even by a topologist's very flexible rules for deforming things, there's no way you can deform that to a point. Similarly for the green one, and you can't deform the blue one into the green one. There's two very distinct kinds of non-trivial cycles here. There's nothing non-trivial on the sphere. That's a global issue, that each of these cycles, if I'm an ant walking along one of these curves, I'm like, I'm on a curve. I'm on a curve. I'm on a curve. I'm on a curve. Each ant, if they just can look at a small portion of this thing, they can't really tell if I'm on this trivial cycle or a non-trivial cycle down here. So this is a very, very common thing, is that mathematicians often make spaces or objects that look very simple locally. They're almost always modeled on a very simple model locally. But the way you patch things together to make a global object can be very, very different. And most of topology is actually about this issue. There's other things that come into topology, but most of topology as a subject unto itself is about this issue. Okay, so I've redone our web of ideas here, that topology, in our sense that I'm going to talk about, is really most interested in global properties. The local properties are usually trivial and uninteresting. Calculus, by contrast, is all about local analysis. It's about taking a microscope or taking a tangent line at a point or looking near every point of some object and looking at how is it curving, how is it bending, what direction is it going in, is it smooth or not. Geometry is kind of a mix of local and global questions. There's a lot of questions of geometry that are local, just how is something curving geometrically, what's its curvature, and then there's global questions. And the global part kind of interacts best with the topology. The local part often interacts best with the calculus. Now you might think, I put question marks here for those words in algebra, you might think, what the heck, these words can't have any relevance for algebra. Algebra isn't a pictorial subject. These guys seem to be where the pictures live. How could there be any meaning here? Well, because there's such tight connections between algebra and especially algebraic geometry, and between topology and calculus, there actually are real issues. There are real ideas here, that there's such a thing as global algebra and local algebra, and the issue of how they fit together. And you kind of import those ideas from the geometry. It's very cool, but I'm not going to say anything more about it. So here's another way to sneak up on the idea of the Hodge conjecture. Remember the idea, we've got like the projective plane, or eventually it'll be a more complicated algebraic space to live in. And so here's the schematic picture. Here's a picture of the cycles that we tend to think about living in the projective plane. So again, we've got an algebraic universe, but we invite a topologist over to just draw a random picture, a topological cycle. So they draw a picture, and then we say, oh, was that legal, even by the topologist definition? It's very easy to make sure that a cycle has the right global property, namely that it's a closed curve, essentially, in this case. Okay, so to be a topological cycle is a global condition, but it's a very easy global condition to verify. Okay, to be an algebraic cycle is a global condition, that the whole thing all at once must correspond to a single algebraic equation, that every single point must correspond to the same equation. That's not something you can check locally. You couldn't just assign a team of 100 people and one person analyzes this part, this part, this part, this part, this part. You couldn't be sure unless you analyze the whole thing to make sure that it really the whole thing really comes from an algebraic cycle. Okay, and it's a much trickier thing to verify that there is some one polynomial that defines this thing, and it's a much more rigid kind of situation. So it would be a bit of a miracle if the bare fact that it's a topological cycle, which is easy to verify, and some easy local condition guaranteed this seemingly much harder global thing to verify, which is that it comes from a polynomial. And that's what the Hodge conjecture says. And so it says, if the Hodge conjecture is true, it's another one of these miracles that we've seen, and we'd like that to be true as well. So that these easy things to verify, some sort of easy global and easy local conditions, somehow magically combines to say, yes, this really comes from a very rigid kind of global object. Okay, this slide is where I'll stop this part of the talk. I just wanted to review a few of the things we've seen already in the web of connections. Bézout's theorem is a great example of topology, which we didn't realize at first it was topological, but that idea of degree of a topological cycle is really coming in, intersecting and seeing how many points of intersection there are. And of course, it's a great connection between algebra and geometry. I've talked about the degree to a topologist. You just take your cycle and intersect it with like a line, and that gives you a number. That's certainly an algebraic object. Differential topology, we've seen a connection there from the idea of transversality, the idea of taking some sort of object and intersect and looking how it intersects and using calculus to really describe that. So we've seen some examples of this, and I want to show you another great example, which is a bit of a different flavor and a little bit of a digression, but I think it's a very worthwhile digression in the next video.